I did not mention it, but in detail, I mentioned a little bit about this time-shifted eternal black holes. If you have questions, we can discuss it later. It's, I think, one of the most controlled settings where these paradoxes can be made precise, because this defines an ensemble of states which are related by large diffeomorphisms. And thus, if the thermofield has a smooth horizon, you have this large ensemble of states that should also have a smooth horizon, and then you run into similar paradoxes. OK, now I will try to explain a little bit how we can use entanglement to go behind the horizon. Now, I don't know, this I have talked about before, so should I continue with like slowly, like what I've been doing, or?
Talked about before, when do you mean?
In various meetings, and some of you have already heard the story, so.
Yeah, you know, I don't think you should assume we.
OK,
Yeah, you just go.
all right. So now the thing that we do with Suvrad is that we sort of use the following logic. So the quantum fields outside the horizon appear to be in an entangled state because they're thermally populated. So they seem to be entangled with something. So they're entangled. This means that since we have only one conformal field theory, they are entangled with some degrees of freedom in the conformal field theory, which the proposal is that these degrees of freedom can play the role of the modes of the interior. Now the question is, how do we identify those more precisely? OK, and now there's a natural mathematical construction that addresses this problem in some sense. It addresses the problem that you have an algebra of operators, and you have a state, and you probe the state with the algebra, and you compute the correlators of that algebra on the state, and you notice that the state appears to be entangled when probed with this algebra. So this mathematical construction will allow us to canonically identify the remaining part of the Hilbert space which plays the role of the modes with which your algebra is entangled. Okay. So I'll start with some mathematical definitions. So we have some Hilbert space and a state psi. So we need to have a state psi in a Hilbert space. So for us, the Hilbert space will be thought of as the Hilbert space of the boundary theory. And we have an algebra A acting on the Hilbert space. So these are the starting points. And we have two assumptions. The first assumption is what is called that the state psi is cyclic with respect to the algebra. The only thing this means is that you can generate the full Hilbert space by acting with elements of the algebra. If you want to be more precise, you may be, in some interesting situations and relevant for physics, you can generate a dense subspace, not the full Hilbert space. But intuitively, for us, it's sufficient that you can generate the Hilbert space.
You say this happens, which is
like I will explain a little bit. Like in a regular space, I will come back to this. No. This is the fundamental Hilbert space of the CFT. So in particular, I do not assume at this point any decomposition of this Hilbert space into interior or exterior or anything like that. It's just the Hilbert space of the n equals 4.
Algebra means you can take products also.
You can take products, linear combinations, dagger. We also want to have a dagger closed under conjugation. Well, I don't know, identity operator. And for the theorem itself, you may have to assume some properties about the topology, like if it's a von Neumann algebra and so on and so forth. But for us, this will not be relevant. So this is the first statement, that we can generate the Hilbert space by acting with elements of the algebra. The second condition is that this state is separating, which just means that you cannot annihilate the state with this algebra. So you cannot find any annihilation operator in the algebra that kills the state.
So for the harmonic oscillator, the vacuum mode.
The vacuum will not do, because you can annihilate it. That's right.
Vacuum would have done if your algebra was just algebra of A daggers. But because you
exactly.
have it closed and then.
Exactly.
So just to make sure, this means that there is no state annihilated by all operators.
No, the particular state psi. So this entire thing is based on two ingredients, like a reference state, which is important, and an algebra. You cannot annihilate this state.
So
You may be able to annihilate other states in the Hilbert
I
space.
see, but sorry,
Yeah.
there is no operator in the algebra which annihilates the state? That's
Yeah.
the claim?
Yes. Of course, any non-zero operator.
Annihilate the vacuum.
That's it. So the vacuum does it.
I will come to this point.
And in particular, in a harmonic oscillator, if you want it strictly to be true, there will be no state. If your algebra
Exactly.
is anything,
Exactly.
there's
Exactly.
No state that's
Exactly. Exactly.
No finite element.
That's right.
Because you with some number
Everything
of
is annihilated by some number of
values.
ways.
Exactly.
Okay.
And the intuition is that in harmonic oscillator, this algebra has access to the entire Hilbert space. There's nothing that this algebra cannot probe. If you take two harmonic oscillators and you put them in a thermofield-like state, and you take this algebra to be the algebra of the one oscillator, then it's satisfied.
Sorry, but the algebra would consist of some. I mean, sorry.
If the algebra is big enough to include A, then it
No,
comes.
no, but it could just.
X, you could try X.
No, it could just be A diagonal, a bunch of A diagonals, product of a bunch of A diagonals.
It's closed under dagger.
It's closed under.
Dagger.
Yeah,
The-
but then you would just have a bunch of A's, so that's fine.
No, but then there's
No,
no,
okay, sorry.
no state that is annihilated by all these.
Okay, let me give you an example where this is very relevant and nice. Yeah.
Sorry, maybe I'm sorry.
Yeah.
You said if you have two harmonic oscillators
And you put them in an it's important that you place them in an entangled state.
in an entangled state, then there is.
Then, and you take this algebra to be the algebra of the first oscillator, then the conditions are satisfied.
So in other words, no operator A belonging to the first algebra will annihilate.
Yeah, because there's always the other side. I mean,
the others.
yeah. If you put them in a pure state, if you take occupational level times occupation level, that will not be good, right? You have to take this an entangled state. You take two spins, just take two spins. Like if you take the state up, up, take two spins, and take the algebra A to be the algebra of Pauli operators acting on the first spin.
Yes, yes.
Then this condition is not satisfied because you can annihilate the state with a raising operator of this guy. But if you take this state, then they are satisfied, the conditions. You may think, what if I raise it twice? I mean, if I try to raise the first spin one time, I kill this component, but I just raise the other one. But if you act the second time, then it seems like you can annihilate the state. But the point that's identically zero as an operator in that representation.
Okay, nice. Thank you.
Okay. Another very interesting example we'll discuss in more detail is and it's actually quite relevant in physics, is Riedler space, Minkowski space, I mean in the Riedler decomposition. So it's a very nice example where this story can be applied. You take the Minkowski vacuum of a relativistic quantum field theory, and we consider the algebra A to be the algebra of operators which are localized here. Yeah. Then it's some theorem that I will mention later. It's very easy to understand for a free field that you can generate the full Hilbert space by acting with elements of the algebra here. I will come back to this in a little bit. So this condition is satisfied. And you cannot find any annihilation operators localized in this domain. I will explain in more detail later.
Again, because of the hugely.
Exactly. Right.
Very interesting. Okay, thank you.
So if I had a single harmonic oscillation and I took an arbitrary linear superposition, I took alpha n n.
Yeah, you might be able to do that. Then you have to be careful about what you include in your algebra. Like you can also take sequences. I mean, you're asking if it has arbitrarily high excitation levels, right? With very small coefficients.
I'll just make it so that the norm is finite, but alpha n doesn't.
Yeah. So then you have to also tell me what algebra what are the elements of your algebra? Can I consider as an element of the algebra which is of the form sum over Cn a to the n with some coefficients? So it becomes a more subtle question then, and you have to define more carefully which elements you include in your algebra once you start considering infinite sequences.
I'll tell you why I was asking.
Yeah.
I was trying to, I mean, as you said, in this thermofield double, you can do it.
Yes.
You have both sides.
Yes.
Now, I was trying to understand whether we could see the same thing intuitively from just one side, as saying that at finite temperature,
Mm-hmm.
all states are somehow excited.
Yeah, I mean that's precisely the essence of what we're going to do. Precisely. You mean the exterior modes, the fields outside the horizon?
Yeah.
Yeah, those are thermally populated.
And so even if you take a to the power a million, it doesn't quite.
You have to be a little bit careful about the n scaling. I mean, you mean 1 million? What is capital N? The SUN.
N is larger than 10.
Okay, then you can do it for exactly.
Okay.
That's
But
right.
that seems like a cheap way. I thought for the Minkowski vacuum it would be more direct, you know, just because it's more like your the two-spin example. That
Yes.
You just have
It's
so much
entanglement, that's right.
It's not that you're going off to infinity in a sense. That is also true.
No, I think Srilas wanted, if I understood, the question was that the question was that you can, wasn't the question that you cannot find any annihilation operators because the field is thermally populated?
Yes, because you keep going.
Yeah, because the state is thermally populated.
Yeah.
But I thought what you would say is even for the lower frequency, even if you restrict it,
If you
it's not because each mode,
no,
each frequency mode is entangled.
if you truncate it, like if you take, for example, the ground state plus the first excited state, a linear combination, an entangled state involving only those guys, and the algebra is the ladder operator algebra, that will not do, right? Because you can act with a squared or a cube or whatever, some high power of the annihilation operator and kill it. In the spin, you couldn't do that because in the spin, as soon as you go to the square of the raising operator, it was identically zero as an operator. So the algebra is different.
At finite temperature, you can either think of it as this artificially double Hilbert space, in which case there will be some very precise kind of statement. There's two oscillators, one.
Yeah.
But also you should be able to think of it from just one side.
Exactly. So
So there is no example for a two harmonic oscillator case where you have a finite number of excitations in an entangled way?
no, I think if you truncate, if you're asking if in this proposition, if you put a cutoff from the occupation level, then the theorem cannot be strictly applied, right?
No, but if it's two harmonic oscillators and then you take just the oscillators of algebra is just one of the oscillators, then you'd be able to do it.
It depends on the state.
You'd be able to find.
I think, yeah. But I think Sandeep was talking about. Sandeep was asking not about the state that you were talking about, which is thermally populated, but if you truncate the occupation level,
truncate
then
for any one side.
or either, yeah, or both sides. Then you cannot do it. Then.
Also, it's not the entanglement that's important.
Well, it's a
Entanglement with arbitrarily high.
yeah, that's right. It's an interplay between the type of algebra that you have and the type of entanglement that you have.
No, but Shiraz was saying if one is just in single harmonic oscillator, if one were to consider some complicated.
Oh, it doesn't have to be thermal state. If that's what you're asking,
not thermal, but just
it can.
up to infinity.
Yeah, that will do.
Then, it's
That-
not clear that there could exist such a state also. Right?
So if you write down,
The entanglement is not playing any this thing here.
no, it plays a very important role in the entanglement. But also, I mean, if you in the harmonic oscillator, I think Shiraz was mentioning states of this form.
No, just with a single harmonic oscillator.
Oh, with a single one.
Yeah.
With a single one. I see. Where
Just
you
the
take.
fact that you are going off to infinity is creating the issue, right?
Yeah. Okay. So if you try to ask something about this, sorry, your point is that you cannot find annihilation operators for this state, right? Is that the question we're asking? Well, then it's also clear because you can start considering operators in the algebra of the form, well, dn, a to the n.
And you cannot do for
Some
if you had
combin-
an entangled thing.
Say
also
again?
You could do this, right? If you had an entangled thing, then also you could let's say enlarge algebra to consider infinitely many n's, and then you will be able to kill the entangled thing also, no? Same way that you will do this because the other side will just be a spectator. No?
Okay, for these questions, you have to be more careful about the definition of the algebra and the topology that you define, like which limit elements you include in that algebra.
Yeah.
And okay, I'm not prepared to answer this question. We have to work it out carefully. We can do that afterwards if you want. Okay, but these are just this is the input of the theorem, right? We haven't told you the statement. Yeah. So this is the input. But intuitively, what this means is that if you have a system and you can probe it with some operators, and if you cannot find annihilation operators, intuitively this means that the part of the system that you have access to is entangled with something else, as we saw in some examples, right? Okay, anyway, so this theorem says that in that situation, the representation of the algebra on this Hilbert space is irreducible. So in particular, you can find operators which commute with all elements of the algebra, what we call the commutant. And the important thing is that this commutant is acting on the same Hilbert space as the one we started with. You don't need to enlarge your Hilbert space. And moreover, this A prime is isomorphic to A.
How do I construct it?
I will show you. I'm just telling you what the theorem says. And moreover, the algebras are entangled in a specific way, in a canonical way that I will explain a little bit.
He's going to explain, but I find very helpful in this, just keep the Plummerfield double. So the state is e to the power A tilde, sorry, A dagger, A tilde dagger, active on vacuum.
Right.
Just keep that in mind and everything.
Yeah. I also like to think about I also like to think about the Ringler space, where A is the right wedge,
Yeah.
and A prime is going to be the left wedge.
But it's very interesting that this just comes out from.
One thing that is important here is that this new algebra, this new operator A prime, which commute with all the previous operators, they act on the same Hilbert space. You don't need to enlarge your Hilbert space. And one way to think about it intuitively is the following. Suppose that we work with a finite dimensional algebra for a moment, just as a toy mode, right? Suppose that the dimensionality of A is equal to n. And we start with the state psi, and we define the span of all states that you get. This is the Hilbert space, right? Now, what is the dimensionality of this Hilbert space? It is equal to n, because we assumed that there are no annihilation operators. So all vectors that you get are linearly independent. So if the algebra is finite dimensional, and if the condition is satisfied, the first one and the second one, then the size of the Hilbert space is n. The dimensionality is equal to the dimensionality of the algebra. But now let's ask, how many operators can we define on this Hilbert space? N squared. So we start with an algebra with dimensionality n, but the set of all possible operators acting on this Hilbert space is n squared. So in some intuitive sense, it means that there is enough space on this Hilbert space to define the second copy of the size n. Okay, this is just an intuitive argument. We're not relying on this argument, just some intuitive idea why we have enough space on this Hilbert space to have two commuting copies of the same algebra.
So what was I didn't understand. The dimension of the space was n, right?
The dimension of the algebra was n, and then we concluded that also the dimension of the space will be n because of the second condition, that all vectors that you get are linearly independent. If there was some linear dependencies, then they would annihilate. They would find annihilation operators in the algebra. Yeah. I mean, this also. I mean, in the beginning, I was confused. If we want to mimic the thermophile double from starting with a single conformal theory, it means that you should start with the Hilbert space of one conformal theory and get the tensor product of two of them. So the dimensionality of what you get should be the square of what you would expect, right? And this sort of explains intuitively why we get this square.
You get the square because you find the commutant, and then you can take arbitrary guy from here and arbitrary.
That's right. That's right. Right. Okay. Now let me tell you how you do this more precisely. Let me know if you should skip this technical part. Should I skip it or I can?
I think since we need to go to the end, anything that he judges we should skip.
Okay.
Especially if it's technical.
Okay. If it's what? if it's. Say again.
Especially if it's technical.
Technical.
Can we, if it's okay with you, can we give Kyriakos up till 1:45?
Okay.
Don't feel like you have to stop at 1:30.
Okay, let me then spend only 2 minutes without going to the details. So the way you derive it is there's a canonical way of doing that, right? So first of all, you define this an antilinear map, which.
So one question. So this confusion is troubling. So suppose can I create a product of the annihilation operators and some kind of linear combination, some complex linear combination, such that it annihilates the psi option?
No, by assumption, this was not possible.
Let's say psi is some energy state of the system, okay? And there is some specific A that makes it brings it to the lower energy state.
Yes.
And I keep track of all those lowering operators, and I create a product operator, and I.
Well, then the assumptions of the theorem would not be obeyed. you would not be able to apply the theorem strictly speaking, right?
So those keeping track is not possible.
Well, we will actually do it. I mean, we will do it, but I will come to this point in a little bit. So strictly speaking, you would not be able to apply the theorem as it stands just by in that situation.
Actually, I'll say one more thing because I remember when I read your original paper, this is what helped me understand. It's, if you just think of the thermofield level and you think of e to the power a prime dagger, a dagger, then you act with a on that because this is a whatever state.
So the squeeze state.
The funny term, coherent state.
No.
Well, it's coherent with respect to a. A dagger is the number.
The full state is squeezed.
Fine. But think of it from the point of view of the first algebra. It's coherent with respect to that. So you act with a on that, and you pick up a prime dagger.
Correct.
So it's clear then that action of a cannot annihilate the state.
Yeah.
Because it's the same as action of a prime dagger.
Yeah.
And it really creates
Right.
the shadow thing.
Right. I also find it. Yeah. Okay. So yeah. So let's see. So maybe I should skip.
The finite dimensional setting also there is.
In the finite dimensional setting,
all the conditions for this theorem are
did you say finite dimensional?
finite.
Yeah. In finite dimensions, you can actually work it out yourself. I mean, all this theorem that I'm going to
What
explain.
was the example, this SU2 example that you said?
The spin thing. That's an example. Yes.
So you're not counting zero operator as.
No. No. In the condition, the zero operator is not allowed to be used.
But what happens if you have an operator squares to zero?
That's okay.
That's not part of an algebra anymore.
No, it is an algebra with some relations.
It will never be satisfied your condition.
No. If the operator itself is identically zero, then we don't mind.
That's not part of the algebra.
No. It's part of the algebra, but
Operator is squaring to zero.
yeah.
So you are allowing those zero operators there.
Non-zero.
When you formulate this condition, you demand that this is non-zero. So your algebra could have relations. It could be that a squared is zero in the algebra. That's fine. And a squared is allowed to annihilate the state. That's not a problem.
But the separability is not defined with respect to these operators. It's only with.
It must be that the operator.
Yes.
Yeah.
Yeah. I mean, S plus square is not what we have in mind when we do this.
S plus squared is identically zero.
Identically
So
zero.
yeah.
Not a non-trivial element of the
Right. Okay, so then maybe I skip some details here. You do some algebraic techniques and you derive an operator J, which is called the modular conjugation, which allows you to find an isomorphism between the algebra and the commutant. And then, so the theorem gives you a construction of this J constructively, and it also maybe what I need to introduce is this delta, which is e to the minus k, where k is what's called the modular Hamiltonian. And an interesting point is that this algebra is closed under time evolution with respect to the modular Hamiltonian, which we will explain in real space has a very natural physical meaning. And moreover, there is some generalized KMS-like condition. You define some formal time evolution with modular Hamiltonian, and you look at a two-point function abstractly, right, on this algebra, and it has some periodicity, which, if you apply it to a thermal system, turns out to be the KMS condition we had before. But this is all pure algebra, right? There's no assumption about physics here. Now, if you want to prove this theorem for a finite dimensional system, you can do it yourself, right? I mean, it does take some time, but you can do it. It's not so difficult. The mathematical theorem was for infinite dimensional algebra, so it was a bit more difficult to prove. So in the case of Rayleigh space, all of this have extremely intuitive interpretation.
Sorry,
yeah.
The theorem, the final thing was that these algebras are entangled in some way.
Yes.
What does that mean?
Oh, the two-point function between, here I haven't shown it yet, but you can also massage this expression a little bit to rewrite it as a two-point function between a and a tilde. I mean, you have a strip where you can analytically continue the correlators in imaginary time. In a field theory, it will be by beta, right? You look at the two-point function.
Sorry, no, I mean this is abstract setting. You have this algebra of operators A and an isomorphic copy of A.
Yeah. So here I showed you that this two-point function is periodic with period 1, I mean, in these units. Normally this would have been beta here, right? But we're working more abstractly here, so it's this one. And this relates the two-point function of A and B to the two-point function of B and A. If instead of I, you go to I over 2, then you get the two-point function between A and A tilde. You get a prediction about the two-point function of A and A tilde. And if you take that prediction and you evaluate it for a thermal system, it turns out to be the two-point function you need between the two sides of the thermofield state.
But in terms of operators of algebras. So if you just think of, compute the entanglement entropy of the state, dividing it out into
this is something we have not talked about so far. Computing the entanglement entropy and of the algebra. We haven't used it, right?
We haven't used it, but wouldn't it be true that it would have a non-trivial entanglement entropy?
Yeah. I mean, it would.
It would have.
Yeah, of course.
So that
It should be related to the.
I'm sorry, I didn't understand the question probably.
you want to know in what sense is the state entangled with respect to these two different
Well,
entities?
yeah. So what I wanted to say is it's entangled in the sense that the 2-point function between a and a tilde does not factorize. It's non-zero. It's not just the 1-point function of a times the 1-point function of a tilde. There's a non-trivial 2-point function between a and a tilde which expresses the fact there's entanglement.
Yeah, but another thing that's also true is that this, if you compute the entanglement entropy of this state, breaking it up into one algebra and the other,
Yeah.
you get something non-zero.
You will most likely run into the usual UV divergences, even from the algebraic point of view. So if this algebra is infinite dimensional, you will most likely find a divergent result. But you could
But
then,
in a finite dimensional situation.
yeah. In a finite dimensional, you can get a.
Shouldn't it be related to the modular Hamiltonian in some way? If you thought of that as.
Yeah, good. So if you have a bipartite system, so if you have a finite dimensional bipartite system A times B in a pure state, this delta turns out to be rho of A.
Is rho inverse.
Exactly, right.
Then literally the entanglement you might associate with this algebra A
Yeah,
would be the form now.
exactly. That's right. Okay, so now the way it's very useful, I think, to think about regular space. At least I like to think about it. So we have this the Minkowski vacuum n a prime, and in this situation, all these operators have a very nice physical meaning. So in particular, let me just tell you the results. This guy S that we introduced earlier is the product of the CPT operator times a rotation around the x-axis times the complexified Lorentz boost by parameter pi. So if you follow the formula, you find that this delta is nothing else but e to the 2 pi times the Lorentz boost generator, which is natural, right? In the sense that you can think of it as a density matrix. Yeah.
Show the formula again for what was this? S was,
Yeah.
theta R1, what is theta again?
Theta is a CPT operator,
R1 was what?
a rotation by pi around the x-axis. This is for 4 dimensions, specifically for 4 dimensions.
Ah.
More generally, you have to do some reflection around some plane. It's quite easy to follow. I mean, it's really, really simple. You consider, I don't know if you want to do it, but I mean, you consider a complexified Lorentz boost. The complexified Lorentz boost by parameter I pi, you can check trivially. I mean, just look at plug-in. It takes the point txy into the point minus t minus xy. It actually maps the right wedge into the left wedge. And then you have to do a few more things.
It's a rotation, right? A rotation.
No, it's not a rotation. It's a complexified Lorentz boost.
But if I went to Minkowski's,
No, to Euclidean, yes, it would have been a rotation. Yeah. Of course. Right.
Yeah, exactly.
Yeah. And then you have to do a little bit more. I mean, because I don't want to go into details now.
There's some messing up that you have to fix.
Yes.
It's basically some,
Then some reflection you face.
Yes.
Something that we do for the fraction of t.
Yeah.
Yeah, but the key point is the e to the power minus pi k.
There are two. Yeah. This is one key point, that delta is this one. And it totally makes sense in terms of this, right? The reduced density matrix of the right wedge is the Lorentz. I mean, if you look at the Unruh observer, the accelerated observer, he sees a thermal density matrix where the Hamiltonian is the Lorentz boost, right? And the temperature is 2 pi. But here we have this rho A times rho B to the minus 1. So we get the Lorentz boost on the right side times the Lorentz boost on the left side, right? So this is the full Lorentz boost generator.
Edge
Yeah.
minus edge.
Exactly.
Yeah.
It's the full modular Hamiltonian, the two-sided modular Hamiltonian.
And by the way, what is J? Will you tell us?
Yeah. J is this one. It's very simple in this case.
Theta CPT times R.
Yeah, it's just the thing that maps a point from here or symmetrically to the other side.
The CPT was needed because it's going to take A to A dash.
Exactly, precisely.
But the theta I can't see.
Well, okay,
The R1.
it's very simple. The definition of this S was that it had to do to exactly. You have to act on a state with an operator and get this operator at the same space-time point conjugated. So that's why you have to add these rotations. Anyway, so in this particular case, this is very nice. And finally, this formal KMS condition that I mentioned is what gives you the Unruh temperature, right? In this setting. But you can apply it to any even a strongly interacting quantum field theory, right? You find that the correlators are periodic in imaginary time with respect to the Rindler Hamiltonian. All right. Now, in our situation, it's a little bit different. Because, so here, the reason we had the subalgebra and we defined this complement of the stuff was because we took physical space and we divided it in two parts. In the case of the black hole, that's not what we want to do.
Yeah, you had Hilbert space was a product of two Hilbert spaces.
Exactly.
So naturally, that was a product of two Hilbert.
Exactly. Now, it's not that we want to concentrate on a small region of the boundary theory, right? We have access to the entire CFT. So you would say, okay, if I have access to the entire CFT, I have the full algebra. There's no way that I can have the commutant. I have all the information of the state, right? In principle. So you may think there's no way to decompose the system, but
Is there a way to find a subset, sub-Hilbert space of the CFT?
yeah, so that's what
with
we.
the setting with the commuter subset?
Well, that's what we sort of try to do.
Okay.
So instead of dividing the algebra in physical space or the Hilbert space in physical space, we think of a division in some sense the space of operators. So we divide the operators of the theory into simple and complicated, and we go to concentrate on the sort of subalgebra corresponding to simple operators. Simple operators are defined as the single trace operators of low conformal dimension, so the operators that are dual to supergravity fields, as well as their small products. Small means that you can multiply them, but the number of factors should not scale with capital N.
Not an algebra.
This is not an algebra, but that's why there are these marks here. But
It's an algebra when it goes to
exactly. But this is a bit subtle because
You're a bit worried about using.
yes, precisely. So this theorem cannot be strictly applied. But I will come back to this point in a little bit. Yeah. Okay. Then we also define instead of working
It's
with.
just like you've got a thermal gas.
Mhm.
It's got all kinds of excitations. No reasonable operator.
Yes, that's right.
I mean, that's quite
Right. But the fact that we cannot define the small algebra in a very clean way is something that is a bit annoying. I mean, we have to define this algebra by introducing this idea of not multiplying not too many operators. It would be nicer if we could find some more clean way to define it. But I think it's very similar to asking when do correlators factorize at large n. If you have a very large number of operators, the correlator may not factorize. If you have a small number of operators, it will factorize. But how do you find a precise, let's say, cutoff between the two regimes? It's not. I don't know how to make that precise. Or if you have a thermal system and you start probing it, it will appear to be thermal for simple observables, but it may appear to be non-thermal for complicated ones. But again, I don't know how to make precise the distinction between the two. So only in some limiting sense, we're taking n to infinity, and in this limit, if we keep the observable fixed, then we can say that this observable will behave thermally. If you fix the observable and then you take large n. So okay, there are some subtleties here, but
So why is factorization of formulas relevant to this question?
no, I'm saying this question, how exactly we define the small algebra, we can think of it as defining as the set of operators which, for example, factorize, for instance. But we also want to restrict their Hilbert space by defining this code subspace. So instead of working with the full Hilbert space, we define this code subspace. Psi is a microstate, and we consider the span of this algebra. So all states you can get by acting on a microstate with single trace operators.
And not too many of them.
Not too many of them. And there are some additional conditions that should not be separated in time by a very large interval, because then, in some sense, they would be complicated operators. So we want to restrict them to a time band of some length, which should be several times the scrambling time, but not like of order e to the n or something like that.
The anticipation is that the one copy is going to be the outside mode and the other thing is going to be
Exactly.
the inside.
Precisely, that's anticipation. So we introduce code sub. Yeah. Yeah.
In terms of the time band, in global coordinates, there's a maximum band, right?
There is a black. There's a black hole in the middle.
There's a black hole in the middle.
So in
now
principle, you could make it. Yeah.
Okay.
I think the worry is that you take single trace operator, but you evaluate it at very late times, it becomes
Yeah.
a very complicated operator.
Right.
And so you can't.
You won't allow that.
You don't want to do that. I mean, you may be able to do that, but to be conservative, let's not do that for a moment. So we will remember in this theorem, we wanted the state to be cyclic, to span the Hilbert space. But here, because we have restricted rotation to small algebra, we will demand that the state generates not the full Hilbert space, but only this code subspace. But by definition, it generates it. We define this code subspace as a span of this algebra.
So just to make sure, you don't quite have an algebra, but you have a set.
I have a set, exactly.
And that's good enough to define h of psi.
Exactly, precisely. Okay, so we define the set of psi, and by definition, this set is cyclic. It generates this set. We define this set as a span. So the first condition is to satisfy. But also, because of these correlators on the pure state are very close thermal correlators, it's clear we cannot find annihilation operators in this set acting on the state psi. Why? I mean, from that equation, if you look at any state of this form, you compute the norm of that state. That's approximately the same thing as trace e to the minus beta h a dagger h, which is non-zero. Because e to the minus beta h has positive eigenvalues, and a dagger a is a positive operator.
But those, so one confusion. So this psi, basically the A span the H set. The
Correct.
small algebra
Yes.
So this psi, if I take all the psi's that are living inside H psi, do they form a complete set?
Of?
So any psi inside that H psi I can write as some basis states.
Yeah, you can write as a linear combination of A1 psi, A2 psi, A3 psi, and so on and so forth.
So
But it's not the basis of the full Hilbert space of the theory.
the basis is the full Hilbert.
No, it's not a basis of the full Hilbert space of the n equals 4. It's a basis of the code subspace only.
Because he doesn't have the full span is not the full.
Yeah, correct. So, okay, there are no annihilation operators, so it seems that this set A sort of satisfies the conditions of being a cyclic, the conditions of this theorem that we started with. Modulo this subtlety that it's not quite an algebra, so we cannot strictly speaking apply the theorem, right? However, there's an analog of this theorem that we can apply, okay, I will say details if you want, but maybe I should skip some details now. One thing you can check, for example, is that if you follow the algebraic steps, you can try to calculate what is delta, the modular Hamiltonian for this algebra in the state, and then you find, using Largen factorization, the KMS condition, that this delta acts on this small Hilbert space in the same way as this operator. So you find that effectively the modular Hamiltonian for a pure state is the CFT Hamiltonian. You want me to say how to prove it, or?
So you're saying what you can show, I mean, you've chosen some set A, and then
Well,
you define
yeah.
delta for that set in
That,
the way in which you had done earlier, right?
exactly, precisely.
This is the antilinear.
Exactly. So I start going through the theorem. I define this S. I calculate a stagger S, and I cannot strictly speaking apply the theorem because it's not a full algebra. So there are some steps that break down, right? But we tried quite hard to quantify to what extent the error terms that you get modify the result. And we think that in the limit where the cutoff, so this set has a cutoff, right? In the number of operators that you can multiply together.
Yes.
If you select what question you want to ask, suppose you want to calculate a particular two-point function in the bulk, right? You fix that question. Then you take this cutoff to be sufficiently large. And finally, you take capital N to be much larger, then all these error terms kind of are suppressed. But this is not, this is not entire, it would be nice if this could be done in a more rigorous way.
And what is E0?
The energy of the state. Was there a question?
What is easy?
Oh, the energy of the state. Okay, anyway, so at the end of the day,
So suppose I take one state from this side and another state from this side. I want to try to calculate the two
well,
limits.
you want to combine together two different code subspaces? Is that the question? Yes, we have done, we have tested. If you try to write down linear combinations of a small number of those code subspaces, things work out okay. So you can combine the operators together in a consistent way. But if you try to do it for many of them, exponentially many in the entropy, then you cannot do it anymore. So you get some equations that define these operators on this code subspace. And the idea is that we only define these operators on this subspace, not on the full Hilbert space of the CFT, because simple effective field theory experiments that you would like to do around the black hole can be described inside this closed subspace. Not all of them. For example, if you have some nonlinear process like the collision of two black holes, which you can actually describe in effective field theory, we cannot do it here, obviously. Yeah. Well, I didn't. I'm sorry, I didn't go through all the details. Yeah, skip some details. So, well, A tilde is given by J, AJ, and J can be written in this way. I mean, you get some square roots of this delta, and another way of saying it is if you want to mimic the correlators that you would have gotten by the thermofield state, these are the equations that you expect. I mean, if you instead of O tilde, if you place O, if you think of it as O left, if instead of psi you think of it as a thermofield state, and then these will be the equations.
Yes.
But they come out naturally from this more general perspective.
But for the thermofield state, this is sort of obvious.
Yeah.
Exactly, it's kind of immediate to check.
Yeah.
Exactly, it's obvious.
So this is O tilde, not dagger, right?
Yeah.
Yeah. I mean, for the dagger, you can also define. I'm sorry, I did not write it down, but you can also write down the equation for the dagger. I mean, yeah.
Yeah, so that's why it's not killing something, it's just going to another state because of this assumption that it's not, doesn't annihilate.
That's right. So I want to emphasize that these equations are consistent. So these are linear equations that define this O tilde, right?
Yes.
This is a set of rules. You give me a vector, and I tell you where this O tilde is maps the vector. Now, it could have been that these equations are inconsistent. For instance, if you had an annihilation operator here, you would get an equation that O tilde acting on the zero vector gives you something non-zero.
You know it can't be inconsistent because these equations apply to the thermofield.
Yeah, I mean, whether they're consistent or not depends on the property of the state psi. For example, if you take psi to be the ground state of the CFT, these equations are inconsistent. So this doubling can only be done if we are around a thermal state, if we're expanding around the thermal state. They wouldn't have, I mean, a typical pure state which looks thermal.
Yeah.
They wouldn't apply if you try to do it around AdS with a few gravitons. They will be mathematically consistent.
Yeah, it's just that with that state, you act with enough annihilation operators, you get zero.
Exactly.
But on the right-hand side, there's a creation.
Exactly, precisely. Okay, so now these operators are state dependent because, yeah.
Sorry, so let's say you have some operator algebra A, right, is defined by the small operators and so on,
Yes.
and now you have defined O tilde,
Yeah.
but would they also not obey this condition of being simple operators?
No, they're not simple operators.
Because what is kind of the nature of these operators?
Unfortunately, I can't. Well, let me make this comment and come back to your question. These operators are defined only on this Hilbert space S of psi by this set of equations, not on the full Hilbert space of this theory. In particular, they depend on the state, meaning that the definition of these operators has a reference to the state. So if you change the state, psi, the microstate, if you take a different black hole microstate, these will be different operators.
That's just because that's the definition which involves sign.
Yeah, I mean, the definition is given by using a state. You have to use a state in the definition. And
Sorry, but can you not just drop sign and say that?
no. That would not be correct. You cannot say because O tilde is, well, for example, O tilde has to commute with O, right? Because they're on the other side. But if you had identified O tilde with this combination, then they don't commute. It's just a fact that O and O dagger conjugated by these objects do not commute.
So they commute on H sign.
No. To compute the commutator, you have to use a second equation as well. So let me write an equation.
So all these equations can be solved?
Yes, all these equations can be solved.
How?
How do we know that?
Yeah.
Well, we have a set of linear equations which are telling me how O tilde, I have a rule here, right? O tilde times any vector in this small Hilbert space. I mean, think about it. Any vector in this, yeah.
In this Tomita-Takasaki theorem, you got an A prime of tilde operators, which automatically had all this property, right? You just had to construct it.
Yeah.
with this,
But please remember, A prime was J, AJ.
Yes.
While this e to the minus beta s over 2 is delta to the 1/2. It's another object.
So why don't we just do it with J?
Yeah, that's what we have done. Precisely what we have done. The only point is that you cannot write J explicitly in this case. That's precisely what we have done. But you cannot write J. I mean, in the case of on Minkowski vacuum, you could write J as some CPT operator times the rotation. It was very clean. In this case, you cannot write it explicitly. In particular, J depends on the state. So delta does not depend on the state. Delta is always the CFT Hamiltonian. I mean, it's given by the CFT Hamiltonian. It's always the same. How it was defined, you mean? Yeah, how it was defined, you mean?
Yes.
Here. So S will be state dependent. J will be state dependent. Delta turns out to be state independent. So in particular, it's important that, as you said before, we cannot cancel this psi and just say that O tilde is the same as that operator. That's wrong. Okay, so these are state dependent.
Can I just
Yeah.
ask you something?
Uh-huh.
In general, even in the case where you had a full algebra,
Yes.
and the definition of what A prime is would depend on the state.
A prime as a set would, in that case, would not depend on the states.
Is that right?
Yes, because in the usual automated excited construction, you don't have a small code subspace. You take the entire Hilbert space. So in that case, A prime would be the same.
Sorry, but the whole theory is based on
So
some reference state psi.
you don't.
Yeah, but A prime is the same. Think about Minkowski space, right? You take the Minkowski vacuum and you calculate A prime. It's the set here, right?
Yeah.
If you change the state, you take the Minkowski vacuum plus a particle, it is still true that the commutant of this algebra is A prime.
I agree.
The mapping J will be different.
I
But
agree.
if you look at the entire set A and where it is mapped, it's mapped precisely on the same set.
What I wanted to ask was how general is that? Does it just, in general, when Tomita Takasaki applies, you have an algebra A, even though you're using a state psi all along the way,
So,
ultimately A
that-
prime is independent?
Right, so one second. When you say A prime, so we have A prime is equal to J, AJ, right? There are two questions that you could ask. One question is, this mapping is sending operators in A into operators into A prime.
Yeah.
Are you asking me whether the image of a particular operator in A into A prime depends on the state? Then the answer is yes.
No, I was just asking whether A prime itself
No.
does not.
Think about Minkowski space. What is A prime is strictly fixed by the algebra.
Sorry,
There will be some reshuffling within A prime once you change the state, but not the set itself.
So changing the state meaning going to another state in this H psi.
No, sorry. If you go to another state inside the psi, then the operators remain the same. So the operators are defined on a subspace, which contains the state psi.
Even here it depends on.
Yes.
Does not depend on.
Does not depend on the
So this is a totally different psi. You're saying if it goes
Yeah. If you take a different black hole microstate, which is completely different, right? Same energy, but completely different microstate, then the set H psi prime would be different from H psi, right?
I see, but here, because you don't have an algebra,
Mm-hmm.
there is a dependence.
Yes. There is exactly. That's right.
I mean,
Yes, precisely.
in algebra, this A prime is isomorphic, right, from theory.
Yes.
To A.
Yes.
So when I do my theory to begin with, I start with psi and an operator algebra A.
Yes.
So how come A prime can depend on psi? Because it's isomorphic to A and A didn't depend on psi.
Sorry, A prime as a set does not depend on the state. The precise mapping from A to A, this isomorphism from A to A prime will depend on the state, but the entire
But
set.
you also were making a statement that as an algebra it depends on state.
In this case, because in this case we're not strictly speaking apply the theorem.
But in the strict cases it's just isomorphic all the time.
Yes, it's always the same set.
In the full case, the algebras are defined without any reference to the states.
Yes, I think you can say that this way.
No, but which, I mean, okay, there's an abstract sense of an algebra just in terms of maybe like a Lie algebra. But you can ask, let's say you have the full set of operators acting on a Hilbert space, right? Then you choose one element psi.
Yes.
Then you choose a subalgebra A of the full algebra. Then you construct your A prime. It could have been that A prime depended, as embedded in the set of all operators acting on the Hilbert space, could have depended on this
No.
choice of psi.
No.
I think he's saying before, if I understand right, take n cross n matrices.
Mm-hmm.
Now we choose an n-dimensional algebra of operators. It's got to be n-dimensional,
Mm-hmm.
satisfying some properties. And then you ask for the commuting set of operators that is just uniquely defined by the operators.
Not by the state, you mean?
Yeah, not by the state. Just
Exactly.
It's a property of matrices.
That's
Yes,
right.
Yes.
And it's important that it's an n-dimensional
Yes.
set of operators.
So this embedding can change over depending on the state. But
What? Embedding meaning map from one operator.
Where in your
no, where is this n squared fit?
See, because
this a prime fixed.
I didn't understand. Sorry.
So let's keep a fixed and change psi.
that's what.
So-
What
Psi.
happens to a prime?
It
Does
stays
it
the
move
same.
around in the n squared?
No, if you vary among the set of psi's that obey the condition for psi with respect to a, then it doesn't change anything.
And what?
It's just because you've got
It's just
it's a-
of matrices.
yeah, it's just a property. I think just some statement about matrices.
Yeah.
That-
Not about the column vectors that it's
When you start.
acting on.
Yeah.
So does that mean that this?
But why is it just a statement about matrices? What is the?
Yeah,
Whether an algebra commutes or not is a property of the commutator of the,
We just want
of the
to find a
matrices.
set of matrices which commutes with every
Yeah.
other matrix in
Would
this set.
every element, is it simply then enough to say the following, that A prime is the commutant, maximal commutant of A?
Yeah, so that's correct, but there's a subtlety. If the situation that Shiraz was mentioning is where we have an n-dimensional algebra and an n-dimensional Hilbert space,
yes.
so then this was a maximal commutant and it was unique, as you said, right?
Yeah,
Yeah.
But
then I
here
don't
it's
need
different.
anything, right? I mean, if all you are trying to say
Here it's a bit different.
given an algebra A, I want to identify its maximal
No,
commutant.
no, but it's
then
different.
I don't have to do commutator.
No, 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 no. Yeah, yeah. Well, you don't have to do that.
What do I need any reference state psi even for?
Wait a second. Because,
Just to
yeah, so this example is different from what we have here. So in that example that Shiraz mentioned, the size of the algebra was the same as the size of the full Hilbert space. There was no space to put the commutant anywhere else, right? I mean, you just look at the maximal commutant. In this case, we're considering a small subspace, the code subspace, on which the algebra A is acting. And we want to find the, let's say, the restriction of the commutant on that subspace. So it's a different algebraic problem.
Sorry, that's always the case. I thought.
I mean,
But
here
we
we
have-
don't have an algebra, so I'm a little less clear, sorry. Okay, but even in a case where you had an algebra.
If you had an algebra, let me say something else. If you really had an algebra, there would be no commutant in this
There's
case.
some assumption about reducibility that is crucial there.
Reducibility of the representation, you mean?
You know, when you stated Tomita Takasaki,
This was an output of the theorem. The theorem, the output of the theorem was that the representation is reducible.
yeah, which meant that roughly speaking, your full
It's like in the thermofield. The representation of the algebra of one CFT is reducible because, I mean, there's a second copy, right? So then you can, for instance, find operators on the second copy with commute with all elements of the algebra. So it sort of violates Schur's lemma, right? So that the representation is reducible.
Okay. All right. Let me just understand. So as long as the algebra is cyclic, so you generate the whole Hilbert space
With respect to some state.
with respect to some state, and separable, which means you don't annihilate any state.
Yes.
No element of the algebra annihilates that state.
Then A prime is simply the maximal commutant of
Yeah. But
the state.
if we apply what you just said to the problem that we have,
But there you don't have an algebra.
exactly. If we did take the algebra, if we just take the full algebra of the n equals 4, we could do that. Then you would be able to annihilate the state by some incredibly complicated combination.
Clear.
So then there would not be no commutant, strictly speaking, which makes sense. I mean, there are no operators which commute with all operators that you conventionally define the n equals 4.
You annihilate each part.
Yeah.
Correct.
And actually, this is a good thing because it sort of it connects with this idea of complementarity, which is the idea that the interior is not really a, like mathematically speaking, independent sector of the Hilbert space. It arises only if you restrict your attention to a small algebra.
Okay.
So one confusion. So suppose in A you are trying to evaluate the time evolution of psi,
The time evolution of psi, yes,
psi state.
yes.
So now
So everything is in the Heisenberg picture here.
so
Okay.
you are saying that using some operators of A prime you can do the same for psi, right?
Sorry, I didn't understand the question very well.
So is this the statement that if you can calculate the time evolution of psi using the operator CA prime?
The time evolution is not governed by the O's. The time evolution is governed by the Hamiltonian. The Hamiltonian is not part of the algebra.
Oh.
In particular, you see that the Hamiltonian does not commute with O tilde. Remember, this was a problematic equation that we had. It doesn't commute with O tilde. So H is neither an element of A or of A prime. It's like the Lorentz boost here, right? The Lorentz boost, the full Lorentz boost is not in A or in A prime. It's on both.
Confusion is A and A prime are spatially separated.
Yeah. Okay. Now, so these are defined with respect to the state and not in the full Hilbert space. You can try to ask whether we can combine together the definition over many code subspaces. And as I said before, you can do it for a small number of those, but you cannot do it for all of them. And one way of understanding that is the overlaps between those code subspaces become very large if you take exponentially many states. And in any case, if you could do that, then you would be able to define these guys globally as global linear operators all over the Hilbert space, and then you would run back into the paradoxes that we mentioned earlier. Yeah. There is another sort of state dependence which is discussed there, but it's not the same one. I don't know if you want me to say anything about it.
Is that the map depends on the state?
You can take different states inside H psi and try to repeat the procedure.
That's what I was, okay.
And then there are some nice results that you can prove. H psi is the code subspace, so it's basically a black hole microstate and all small perturbations around it. So you could start with a non-equilibrium state.
Sorry, now we're talking about Tomita-Takasaki, right?
Yeah, in the Tomita-Takasaki.
There's no code subspace.
No, yeah, I'm sorry. Yeah. So the question then is that if you start.
It's supposed to be all of it.
Yeah, exactly. Yes.
Okay, so
Yeah. So I meant in that the discussion there is that you start with psi and then you start with some unitary acting psi and this is psi prime, and if you repeat the same story starting with psi prime, what are you going to get, right?
With the same algebra.
With the same algebra.
I thought you told us you got the same A prime.
You get the same A prime, but J will be different. So the precise mapping is different.
That's the same.
Delta will be different also.
Delta,
It's different. Even the delta is different. Yeah.
I mean,
Yeah.
it's the equality of states, not the individual mapping that gets.
Yes.
But the A, is it clear that it's the same A? So you start with, let's say, H psi.
When I discuss this type of state dependence here, I meant you keep A fixed, and you change the state, and you see what happens.
And any state of H psi will obey this fact that A will not kill it. Maybe it will.
Any state inside psi prime, you mean? No, not necessarily.
No,
It's
but
not.
You created H psi with an element of A.
Yeah.
Now, any element of A will not kill it again, right?
No. It's the algebra is not necessarily invertible, right? You cannot always find an inverse. So you may be able to find elements inside a psi which are actually annihilated by the algebra.
In fact, we can work out how J and S.
Yeah, you can work it out. That's right. Yeah, okay, but let me try to accelerate now because I want to make some new statements. So the point is that these equations are defined in a restricted sense on a code subspace. So this commutator seems to be 0 by these equations, but it's not an exact statement. It's true only inside this subspace. Now, another important point is that this entire construction was based on the idea that the particles seem to be thermally populated. But if you look at the occupation level of those particles, they're suppressed by Boltzmann factors. So if you take this frequency omega to scale like, for example, n squared, this number is incredibly close to 0, right? And it doesn't make sense anymore to think of this mode as being thermally populated, meaning that there are other terms that we have ignored which are much bigger than this number here. So the estimates that we're making in this construction are not reliable if the frequencies that you use scale with n. Okay, so this means we will introduce a cutoff that I will call omega star in the allowed frequencies.
Already begin to break down if omega scales like log n.
It could be even then, yes. So to be conservative, I will just demand that omega star is fixed, and then we take n to infinity. It can be as big as you want, but not n dependent for now. So there's a limitation in these frequencies. There cannot be anything. In particular, we cannot reconstruct a local operator in time, O tilde. I mean, we cannot define this object, O tilde, as a function of t. It's in coordinate space. That requires arbitrarily high frequencies. That's good, because if you were able to do that, it would be almost like being able to reconstruct a second conformal field theory with locality properties, with an OPE, with all this stuff. I mean, you can do it to very high approximation, because you can take this omega star to be very high and then send n to infinity. But if you want to probe distance scales with scale like n, then you cannot do it. I'm sorry, is it, should I explain this a bit more, or is it? Okay.
Sorry,
Yeah.
even with the state dependence from previous arguments, it was that typical microstates you wouldn't be able to find O tilde, right, for a typical microstate.
Well, now this O tilde is state dependent.
Yeah, even with that, for a typical microstate you wouldn't have been able to find, right? Because
No.
of the previous arguments.
No, the previous
they
arguments.
follow any state
So all of the previous arguments cannot be applied anymore.
Why not?
Well, in all of the previous arguments, if you remember, we constantly use arguments involving the trace over all states and some operators here, right? And we derive some paradoxes, like the trace was negative and things like that, right? If the operator here, sorry?
Even the fact that the entropy is decreasing, you said, right?
Yeah, even that can be understood.
So
It's
so
the-
that's
it's
so you're
decre-
saying that
It's decreasing, but it's not a unique map O tilde. There's not a fixed linear operator that takes this entire Hilbert space into that one. There are many linear operators that map subspaces of this Hilbert space into subspaces of that one. That's consistent. There's no problem there, right?
But somehow you don't want to allow O tilde to kill a state, right?
Yeah, and this we have ensured by this equation here.
Just to understand it properly, suppose I took the large n gauge theory at finite but large n.
Yes.
I took all the single trace
Yes.
operators, but I allow, after some time, because n is finite, you don't get independent
Yes, that's
operators,
right, that's right.
You have the stringy equivalent,
Right.
whatever. So I take all the single trace operators which are independent.
Mhm.
This is not an algebra, I guess.
Yes.
And the product itself of two single, this is an algebra, if I allow the products? No,
Strictly
suppose I
speaking,
double
not.
trace.
Yeah.
Because it's where trace identities kick in. So let's say trace identities kick in first at n. If you take 3/4 n times 3/4 n, the product will
Mhm.
go over.
And so you'll get multi-trace operators.
You get the operators that where the trace identities have kicked. You want to restrict to those where it didn't.
Okay, I should ask this later just to understand from you all. But what I mean is, if after taking a trace of sufficiently large number of insertions, you're not getting an independent single trace, that's fine. Then that's not part of the independent set of single trace operators, right? But,
Can I say something? I think there are two issues.
Okay,
The first issue is that
You should go on.
some technical approximations we're making rely on the Larsen expansion. So in several places we're saying, okay, this term is suppressed by 1 over n. If you start using these very big operators, we can no longer control that object, right?
Yeah, that's true. I was just wanting to ask whether I could at least phrase the following question in a sensible way. Is the set of all independent single trace operators at finite but maybe large n, is that an algebra? You would say not even that.
No, I mean it is, but it includes everything. In some sense, it includes everything.
That's what I want to ask. Does it include everything?
I think so, because you take arbitrarily large single trace operators, because of trace identities, you get all multi-trace operators.
Yeah.
So the multi-traces are just part of
Part
the
of the same
products
thing.
of.
Yeah, so you're not restricting in any way.
Yeah.
Okay.
Yeah.
So even with the state dependence, this
Go ahead.
Go ahead.
this H psi
Uh-huh.
code subspace is the subspace for which your construction is valid, right?
For every single H psi, there is some operator O tilde.
Yeah, so you have given a microstate.
Can I say?
Above that there is some H psi.
Yeah,
for
exactly.
which
Yes,
this construction
that's right.
is valid.
That's right. That's right. That's
So
right.
those are the atypical microstates for which you can find that there is.
Whoa, wait a second.
entangled copy.
First of all, I want to make a remark that's sometimes confusing. If this is psi, the state psi, eighth of psi is not the same energy. So eighth of psi should not be thought of as a subspace of states of that energy. Eighth of psi goes both up and
Yes.
so if these are the states of a given energy, eighth of psi is oriented differently, right? Because you can increase the energy by adding a particle, or you can decrease it by removing a particle, right?
But only for
Yeah, but psi is a typical state. I mean, it can be any state. I mean, for every single psi in the original subspace here, you can define an h of psi. So in that sense, we define this O tilde for a typical state. I mean, in the sense, not in the sense that there's a single O tilde that works on a typical state, but for any given state psi, you can find an h of psi in an operator O tilde of that.
So could I ask
Yeah,
a intermediate question?
Yeah.
If we were in Euclidean, is it true that large n factorization breaks down if I bring the operators
To close.
to close?
I think we have discussed it before, and I think you convinced me that no, in Euclidean it doesn't.
Yes.
But I think if you analytically continue to Lorentzian and you somehow boost them on the light cone, you make sure that they collide with very high free energy, then it may break down. Okay, so
As the person who's been interrupting a lot, let me just say, I think we're at 45 minutes.
yeah.
So we should
Yeah.
let you get to some of
Yeah. So this algebra is not really an algebra, so this theorem cannot be applied, and this A prime is not an exact commutant. But here I want to make this point that from a physical perspective, this is not like something that we shouldn't like, because it's what we expect from the idea we discussed earlier about complementarity, which means that the commutant arises only once you restrict your attention to small, simple operators. And fundamentally, it's not an independent part of the Hilbert space. And also, as we will see, there's some non-locality inherent in this construction because this commutator here is not exactly zero. It's zero only in the code subspace. And finally, I remember one of the intuitive arguments that I mentioned is that it's very hard to understand how a typical state can have the correct entanglement. Well, the way we are going around this problem here is that we actually define these operators by the entanglement. So by definition, that problem is not an issue. Okay, now, so in earlier work with Subrat, we mainly concentrated on what happens to the falling observer. But once you start using these O tilde operators, it's natural to consider the question of whether you can extend the space-time, not only in the interior, but in the extended Penrose diagram. So once you start using these O tildes, it's not so natural to restrict your attention only to this part of the space-time. You can ask, where did they come from? So, a conjecture is that the geometry you should associate to a typical black hole microstate is this one, which is part of the two-sided geometry. There is a cutoff here, right, which is coming from the following consideration. Remember that we define these operators O tilde only for frequencies lower than omega star. There was a bound we introduced, right? The bound came from the fact that the Boltzmann factors told you that these modes are almost in the ground state for very high omega, right? So these O tildes cannot be defined for arbitrarily high frequencies. This means if you try to reconstruct the space-time very far towards the left asymptotic boundary, you would need very high frequencies. Just because if you want to focus a wave packet, to concentrate a wave packet in the bulk very near what would be the left boundary, you would need very high frequencies.
So if you're cutting off very high frequencies, how you account for the total entropy?
Entropy. I'm not sure. I haven't said anything about the entropy.
You're cutting out these frequencies only in these fake modes.
Yeah.
Not of the physics.
Yeah. That's right.
But you're saying something about what someone falling inside will see?
Yeah. So what we'll do later is so the conjecture is that this part of the space-time has some physical meaning. Okay. So what we're trying to do is we're trying to excite this part of the space-time, and then an infalling observer would be able to detect that excitation. Right? Okay, so that's clear. So now I think I have to finish in 45 minutes. So let me try to wrap it up somehow. Okay, the intuition of what we want to do is the following. We want to test this proposal, right? So what we want to do is to start with a typical state, excite this region, create a particle here. This particle would normally fall into the singularity. If you send an observer, an falling observer, and you use an ASKLL-like construction, and you calculate the correlator, you will find that this observer will see the particle. But it would be nice to have some more direct evidence in the sense that this sort of evidence that we first excite this region and then we detect the excitation by the ASKLL assumes that we can reconstruct the space-time here by the ASKLL. So what we're trying to do is to exploit some recent developments related to traversable wormholes, which allow one to create an excitation behind the horizon, and then by generating some negative energy shock waves, it can happen that this excitation can get deflected and get detected directly in the CFT. So that's the intuition. So we'll try to first excite this region by time-dependent perturbation, and then perform an analog of the Gauss-Jaffe-Rule protocol to allow this excitation to get detected in the CFT, to escape the interior.
So you'll describe this, but will you literally turn on some kind of double trace deformation?
It will not be double. So the experiment we're trying to do is this one. So should I review this? Now I have many slides here about this Gauss-Jaffe rule. Is it something I should explain a little bit, or? You know it. Okay, very good. So then what we'll do is we will excite the left region by acting with an O tilde operator at some time, and normally it will fall in. And then we will generate the analog of this shock wave that this guy considered. But now it's not a double tracer anymore. It's something of a form O tilde.
Yeah, that's the natural one. Because
that's the natural one.
O tilde is the other.
Right.
That's what I meant by the double.
Oh, okay, sorry.
Yeah.
Would have been double tracer.
Yeah, exactly. So now you can explicitly calculate the stress tensor which is produced here by this perturbation. This is totally reliable. You can really calculate this object, and it has negative energy. It's exactly the same calculation as the one that they did. What is more conjectural is that at the same time when you do this perturbation, you are producing a shock wave in the region that is hidden behind the horizon. If you follow the ASKLL construction, then that's what you get. But of course, that's an assumption that we can use ASKLL in the left region.
But you probably don't even care, right?
Yeah, we don't care about the effect of this shock wave.
Yeah.
We care mainly about the effect of this guy.
Yeah. Because the probe is going to scatter off that.
Exactly. So, okay, so then what we're doing, the sequence is the following. We first create the probe by some operator phi tilde, different from that one. These are different operators, right? We create a probe that will normally fall into the singularity, and then at a later time we do this perturbation by O tilde, and then what we expect from this Penrose diagram is that a probe will be detected in the CFT at some particular time t.
This is just a genuine scattering experiment.
This is a scattering experiment, exactly.
Of something that has negative. Locally it has positive energy.
No,
Locally
negative.
it has negative.
That's right.
So it's not quite an S matrix.
What do you mean locally? As measured at this boundary, everything will be positive.
No, just in the local rest frame at the place where they.
Yeah, I mean, you integrate this null energy along this guy. It has a negative. Yeah.
I can take a little Minkowski bubble there. Is this a scattering experiment or not? Not.
I'm not sure why you say that, because the asymptotic state is not very well behaved.
No, just I'm forgetting about asymptotic. Just locally, do you see that there's two positive energy guys coming and banging each other?
No, one has negative energy, right?
And there's no such thing. I mean, locally. So
Well, in classical physics, but if you use this Casimir kind of contributions,
It's not particle color.
no. Well, some excitation of the field. I don't know if.
Yeah.
And here the sign of G is crucial.
Yeah, the sound is crucial. But the important thing is here is that to some extent well, it's not entirely true, but we have somehow we don't need to talk about local operators in the bulk. It looks a bit more like some statement about correlators. Well, this guy is a bit mysterious, of course, but it looks like a correlator of operators in the CFT.
It's kind of thing that would have caused causality violation had it been possible in some more simple setting.
I don't think it causes causality violation. You mean you cannot form closed time-like curves if that's what you're asking.
Because of the complicated Penrose diagram.
Exactly, that's right.
Had you been able to do this locally,
Yes,
compound many of these, you
that's
would
right.
get causality
Right.
violation.
But in this particular setting,
So it needs the global setting.
that's right. Anyway, so this diagram, if we conjecture this Penrose diagram, this makes some specific predictions about a correlator of this object on the state size 0. So this correlator is basically, let's say, we first of all create the excitation by phi tilde of minus t, and then we perturb the state by this double trace perturbation, and we compute the expectation value of the probe at a later time.
Could I ask you, if you take that blue line which was near the event horizon and you bring it, even nearer the event horizon, does that time separation increase?
If you bring it near the horizon, you mean it will be boosted? it will probably increase, but you don't want to do it too much because then the collision will be ultra. I mean, you want it to be hard enough, but not too hard. The collision.
But I was just wondering whether it behaves like normal S matrices behave. That is that at higher energies they get displaced.
That's right. That's right. That's right. So you don't want to send this guy too early. If you send too early, then the deflection.
Reliability of that.
That's right. So anyway, yeah.
Phi tilde are CFT operators of the same relation.
Phi tilde are tilde operators, like these mirror operators, right? But they're different from O. They're different types of particles. So if this Penrose diagram, this conjecture Penrose diagram, then makes some particular prediction about this correlator. It makes a prediction that at some time scale of order of scrambling time in the CFT, you will get a bump, I mean a signal in your correlator.
Oh. You need scrambling time because there's a 1 over n in that?
Exactly. This interaction has a 1 over n, but due to the time separation, the energy is boosted, so you offset that 1 over n. So there's some 1 over n correction that you want to enhance in order to see the effect. And this happens at scrambling time.
It's 1 over n because it's some connected correlator, right?
Yes, that's right. I mean,
Newton's constant.
that's right.
Oh, yeah, in the bulb.
Yeah.
Yeah. Okay, now let me try to summarize quickly. So this similar experiment was, of course, analyzed by Gauss-Jeffreys Wall and later Maldacena, Stanford-Young in some papers, so in the thermophile state. And we have a similar experiment in the one-sided black hole, right? Now, we'll try to relate the two correlators. The correlator which is the diagnostic of this experiment here with the correlator that is the diagnostic of this experiment in the one-sided case, right? And the point is that in both cases, it is a correlator of this form. It's something of this form. The difference is that in the thermophile case, instead of O tilde and phi tilde, you have left. And instead of psi 0, you have the thermophile state. Now, using the defining equation of the thermophile state, suppose this is the thermophile state here, and you have O left, O left, O left.
I'm getting confused.
Yeah.
You have a single-sided.
No, now we're comparing. Yes, we have a single-sided.
Thermophile state means what?
Yeah, I'm trying to use.
Have you done the analog?
Yeah, I'm trying to compare what Gauss-Jeffreys Wall did in the thermophile state, in the two-sided black hole, to what we would get in the one-sided black hole. And I want to demonstrate that the correlators are very close to each other in the larger limit. So in particular, if somebody has proven that you can traverse this wormhole, the thermofield, this will imply that you can do the same thing for the one-sided. And the way to prove it is, okay, it's a bit technical now. So first of all, in the thermophile state, you will have left operators here, but then you can commute them to the right operators. And by using the analog of these equations for the thermophile state, remember, when we wrote down these equations, we said that there are similar equations for the thermophile state, which is sort of obvious, right? You have all left acting on the thermofield is this and this and this and this.
Correct.
They're the same set of equations.
Yes.
So this means that you can use those equations to move all the O left operators to act on the thermofield, and you slowly convert them into right operators by recursively applying those equations. After doing that, you get an extremely complicated string of operators which are all localized on the right CFT. And you need to take the expectation value of that string on the thermophile state. But that you can actually evaluate on a single conformal theory by tracing out the left CFT. So at the end of the day, the correlator that this guy studied can be phrased as a thermal correlator in the one CFT of some very complicated string involving the probe phi and the perturbation O. Now, we can do the same thing in our case by using the equations I wrote earlier, and we get exactly the same string of operators because the equations are the same. The only difference is that now we are in a pure state psi 0 while they were in the thermal state. So if we can prove that these two are close to each other, then we get a prediction that we have the same phenomenon here, right? Now we can do a little bit better. We can actually, I already mentioned the theorem yesterday that this correlator can be approximated by the macrocanonical correlator up to exponentially small corrections. So in reality, we don't need to compare these two. It is sufficient to compare these two, the canonical to the microcanonical.
So there will be 1 over S correction between these two as opposed to.
Well, yeah, naively we say there's 1 over S correction, but as I mentioned on Tuesday, even though this sounds trivial, I don't think you can prove this statement for arbitrarily. You have to make an additional assumption about the nature of the observable to prove that. So here it is. We have this complicated string, and we want to evaluate on the canonical, the macrocanonical. And a necessary condition for this Penrose diagram is that in the larger limit, these two correlators are the same, provided that we keep these low frequencies that I mentioned. Now, how do we prove this statement? It cannot be proven as a mathematical statement because if you calculate the trace distance between these two density matrices, which quantifies to what extent two different density matrices can be distinguished, it is close to maximal. So you can always find some unusual observable that will distinguish between the two ensembles. So whether this approximation is a good approximation or not depends on the nature of this observable. Does it behave in a nice way when you go from the canonical to the macrocanonical or not? And the reason it's not entirely obvious is because this object is a complicated observable that you get by multiplying operators which are separated by scrambling time. So it's also related to the question whether this observable obeys the Eigen's thermalization hypothesis, which allows you to go from one ensemble to the other. Okay, so there is some technical. So
here it's more tricky.
yeah, but I think the important point here is that we have phrased the condition purely in terms of CFT operators without any reference to O tildes. So whether these two are close to each other can be checked in principle independently. It's a CFT statement. It's not a statement about the O tilde operators anymore. This is a necessary condition that it's not a sufficient condition, but it's a necessary condition for the consistency of this geometry that I presented earlier. So somebody who was able to calculate these correlators will be able to check this. Right? It's a well-defined CFT question.
All those manipulations that this is the hard to reject it, but where you started with your state, but then when you started computing two-point functions of O's and so on, you start getting beta. That was because we were saying that a canonical ensemble does give approximately.
Yes.
I mean, that's all okay in the context where you have these OTOCs with.
Yes.
That's all okay with this chaotic type of behavior.
Well, that's related to that. I mean,
there's some chain there which is kind of.
yeah, exactly. But that's related to what I want to say here. That the interesting physical effect came from the 1/n² corrections, which were enhanced by these exponentials, right?
Yeah.
And what we want to show in the previous kind of this condition that I mentioned is equivalent to saying that these 1/n² corrections, which were enhanced due to these chaotic effects, have to be the same in typical pure states and in the thermal ensemble. And as far as I know, nobody has studied this question precisely, whether the chaotic effects are the same in a pure state or in an ensemble. It's not obvious in the sense that you start with a 1/n² correction, which would in principle be different in the two ensembles. But then after time evolution, this 1/n² correction becomes an order 1 term. So the question is, when it becomes order 1, does it have to be the same in the two ensembles?
That I understand, but I meant just the mapping, the fact that the two-sided case got mapped to a single-sided one. Those manipulations, and therefore would agree with your own sort of expression, which is single-sided. There are no additional issues to worry about if you're dealing with these type of correlators.
No, there are no issues there.
If you try to run the Maldacena and company argument, just starting with a state.
The SWK argument, you mean?
No, Stanford, Schenker, Maldacena, the chaos bound.
Oh, the chaos bound, yes.
They needed this strip. So is this basically equivalent to saying that the width of the strip is the same?
Yes, that's closely related. And this, I think it is related to this comment that we want the proximity of these two correlators in the complexified domain. But, I mean, this would have been maybe beta, not beta over 2. But so naively, if you try to compare a pure state to a thermal ensemble and you try to analytically continue, you may worry that even small deviations will get exponentially amplified, right, when you go on the complex plane. However, this is very important that we have this frequency restriction. So we want to match these two correlators only for modes with frequency omega, which is bounded by omega star, which is not allowed to scale with n. And in that case, I think you can show that if you have two signals and they agree on the real axis up to some error bound, and then if you try to analytically continue them, but you make sure that you only select the low frequencies, then they continue to be close to each other in a strip which can be taken to be beta. In general, correlators on a pure state, when you analytically continue them, they can become very different from the thermal correlators if you go far enough.
So regarding the eigenstate probabilities.
Say again?
Regarding the
EIs are the eigenvalues of the Hamiltonian, not of chi.
Yeah.
That's why we have off-diagonal terms.
No, basically, if chi is changing Ez, for example.
If chi, what?
Chi is changing Ez to some EI prime. In that case, does this relation hold?
Well, this relation is telling you that the matrix elements on different energy eigenstates have to have this pattern, right? This is supposed to be true for single trace operators, but it's not clear whether it's true for this type of complicated observables. So let me try to close. I mean, there is only partial evidence. Let me mention these two things. Some people have studied this question. So they have studied quantum chaotic effects on pure states by using these large T techniques, the Virasoro identity block. And they have argued that indeed you get the same chaotic effects on typical pure states as you get in the thermal ensemble. What we did is some numerical stuff in the SYK model. So we considered the SYK model, and we considered some correlators, and out of time order correlators, where these are the fundamental fermions, right, and some configuration. And we sort of plot the result that you get in the pure state, typical pure state, and in the thermal ensemble, and they seem to be good even when, I mean, here, for example, there are two curves that you don't see. There's a red and a blue one, but they're on top of each other. It's some out-of-time order correlator on the SYK model on a thermal state, thermal ensemble, and on a typical pure state. And they seem to be very close to each other, even in the regime where the chaotic effects have become important. So, okay, or if you calculate the matrix elements of this object when t is of the order of scrambling time.
That was done numerically?
Numerically. You find that the matrix elements are sort of stable, which is consistent with ATAs. Okay, so there's some partial evidence, but there's no proof here. Let me just mention some connection to the Kurkulu-Maldacena story. So what these guys did is that they look at the SYK model, and they introduced the spin operators, which are products of fundamental fermions. And then, first of all, let me tell you how we can actually write down the mirror operators of the SYK model. You select a typical pure state. You run your code, and you generate a Hamiltonian. So we take particular J's, fixed J's. So we really have Hamiltonian that you can write down in Mathematica. And you find the eigenstates. And you write down some typical random superposition of energy eigenstates in a window of energy which is around here, let's say. Then we define the code subspace by starting with the state size 0, and then by acting on it with all these spin operators, up to where you multiply them together up to some cutoff k, which must be smaller than capital N. So you can actually do this. And then by writing down these equations, you can represent these operators as tilde as matrices in Mathematica. You can just do that. So you can have a concrete implementation of these operators in the SYK model. You can even test them numerically if you want. And what Kurkulu-Maldacena did was that they considered a class of states that they called, they denoted in this way. So these are eigenstates of the spin operators. And so you have the spin operators, which are fermion bilinears. And they demand that these guys these states are eigenstates of these operators. So these are the eigenvalues. And they form a complete base of the Hilbert space. But if you take a state which is an eigenstate of the spin operators, it will typically be in the middle of the spectrum. So a typical, if you take such a state, BS, is going to have energy which is centered around here.
So it's not going to be coherent state type of state?
Coherent. What do you mean by coherent now?
You are building up your Hilbert space, the code subspace, by action of a spin, right? Spin operator.
Oh no, sorry. Now I sort of I'm sorry. I'm going a little bit too fast. Maybe I mentioned how we construct the mirror operators, and then I switched gears a little bit, and I started talking about what these people did.
Yeah.
So there are no mirror operators here. They just consider these states in the SYK model, which are eigenstates of the spin operators. And what I'm saying is that if you take the state by itself, it's going to have energy which is close to 0. But then they act with this time Euclidean time translation by beta over 2, which lowers the energy of the state. So you get a class of states which have energy which is close to, in the regime where the SYK model becomes strongly coupled. and they're labeled by the spin operators, by these eigenvalues of the spin, sk. In fact, these are an overcomplete base of states of the Hilbert space of low energies. Right? Okay. And then they argue that the physical interpretation of the states from the bulk point of view is that you have so they calculate correlators and they find that diagonal correlators are time independent, while off-diagonal correlators of fermions are time dependent. So these are not equilibrium states. These are atypical non-equilibrium states. And the conjecture that the Penrose diagram looks something like this. So this will be the analog of the exterior of this YK. And then there's some shockwave here where the space-time terminates, and there's some region behind the horizon. There is some region behind the horizon. So there's smooth space-time. They argue, okay, of course SYK is not geometric, and there are all the subtleties, but okay, in some sense they argue that there's some space-time behind the horizon.
And that, why does that follow from here? Just sorry, I'm not able to.
Well, okay.
Because they construct mirror operators.
No, they don't talk about mirror operators. First of all, they show that if you look at diagonal correlators, so psi I t, psi I of 0, on that state, they show that this correlator is exactly the same as the thermal one, at least to leading order at large n.
Okay.
And you construct the geometrical background by taking these bilinears and combining them in various ways. So they argue that the geometry will look the same from the exterior perspective on the states, outside the event horizon.
For these states.
For these states, right? For these states.
For these states.
For these states.
For these states.
Yes, but they also calculate off-diagonal correlators,
And those are.
explicitly time dependent.
So therefore, you say of some time dependence are going inside.
Yeah.
And how do you conclude from that some part of the
No, well,
behind this?
well, a conjecture is that since something is happening, but it's not visible in the exterior, a natural conjecture would be that it's behind the horizon.
Why is it not visible?
Because the idea is that in the exterior you can probe only these
The
singlets in some sense.
They are.
And okay, and in the second part of their paper, they actually give some evidence. Yeah.
And what is the evidence that it's smooth geometry behind the horizon? Is there some evidence for that?
Well, I think maybe the evidence is coming from the second part.
For the outside means smooth.
No, maybe from the
I
second.
mean, to the extent that you can trust the analogy.
Yeah, I think from the second.
Something happening is not very good.
From the second part, I think.
Yeah.
So the second part is that, in the second part, they, in addition to starting with the states, they consider a perturbation of the CFT Hamiltonian by operators which depend on the microstate.
Hello.
So they perturb the SYK Hamiltonian by an operator which is the sum of the spin operators multiplied by the eigenvalues of this particular state. And then they sort of go back to the to this Schwarzschild description, and they compute the effect of this term on the equations that you get for the Schwarzschild, and then they calculate the back reacted Penrose diagram because of that perturbation, and they argue that basically the new geometry can be thought of as the boundary extending higher up, which allows all these particles behind the horizon, this region behind the horizon, to be visible in the CFT.
Is it related to the scattering?
This scattering, I'm not sure. I mean, this is a little bit more than that, I think, because, yeah, I will come to your question in a second. And what we showed in this paper is that this perturbation is exactly reproduced by starting with the SYK mirror operators that we defined and acting with this type of perturbation. So it's consistent with what the other story we had for the typical pure state.
So is the Penrose diagram like an evaporating black hole? Whoever it gets.
I don't know how to think about it. I mean, there's this guy with a singular. This shockwave is supposed to be singular, so the space-time sort of terminates there. The reason it terminates there is because they have excited all fermions. Here they have projected on all fermions. While in the perturbation we were doing, we were exciting a small number of single trace operators. So in the limit where we sum over many of these guys, the space-time will start to look more and more like this one.
So here, I mean, in your case, these O's were just SKs, right, essentially?
Yeah, these were SKs and these were SK tildes.
Yeah, so
Right.
it produced the effect of just SKs.
Yeah, actually, if you act with Hamiltonian, what you find is that it gives you the combined effect of giving you a state of this type by projecting on the eigenstate of this part, and it places this eigenvalue there, so you get precisely this term.
What are your O tildes? You
Yeah, I'm sorry, it was too quick. They will not be explicit. I mean, you mean this kind of thing?
Yeah.
It's just a solution of these linear equations that I mentioned earlier.
It's not a.
You cannot write them in terms of fermions.
That's what I was wondering.
Yeah, no, you cannot. But you can write them as matrices, like numerically, explicitly. You can take a particular realization and you can write them down.
I see. And then why is it that your O tilde thing was the same as SK, little SK capital?
Well, our thing would be SK tilde, right? And then, well, you can sort of rewrite the perturbation by this effect in a sort of combined way, where you first project on the eigenstate of this operator. And this gives you this state, including the factor. And then the perturbation collapses to this one.
I see. It's because your construction of O tilde had some e to the minus beta h over to.
But the point I want to make is that this comes out naturally. I mean, the connection is quite natural.
So maybe this is what you think. They summed over all k.
Yeah. So they could have done something less dramatic. So the sum over all k would allow them to expose the entire region. Remember, in the experiments we were doing before, we wanted to extract one particle. So it was a small perturbation of the black hole geometry. What they're doing is the opposite limit, where you sum over all of these k's, and you expose the entire region behind the horizon. On the left side, what would be the left side?
And how did they argue you expose the region?
Well, they go to so they take this distortion description, the distortion effective theory, which allows you to calculate this geometry without the perturbation, and then they add this term, and they see the effect of this term.
So they just solve the equations.
They solve the new equations, and they find that effectively this boundary dynamical degree of freedom extends higher up the Penrose diagram, so it sort of has access.
So this part couples to the Schwartzian.
Exactly.
Changes the Schwartzian.
Yeah, that's right, precisely.
I see.
Yeah. So yeah, but in the limit where we take this perturbation and we take more and more of these guys, this starts to become more and more like that one.
The eigenvalue to O tilde are SK because of this isomorphism.
Yes, that's right. Okay, I think I have to wrap it up, right? There's some connection with this story, but it's important. Okay, yeah, I think I can stop here. Thank you.
Any more questions? I'm glad you didn't go through that part, because I thought it was an accomplishment that Bob and Alice were not mentioned.
Let me see if
Bob was the guy going through.
do I have these words?
Appeared on the other side.
There is no Bob.
Bob gets me irritated.
There-
Bob and Alice are on a shoot.
There's no Bob and
But it's
Alice.
such a nice example of teleportation being
Yeah.
justified by love.
Okay.
You don't like that? I see. Okay. Maybe over, I may not be able to join for lunch, but just what was a little unclear was, I mean, the way the whole Tomita Takasaki, etc. story was working had a lot to do with entanglement.
Yes.
When you have the single-sided case,
Mm-hmm.
then I mean, if in the end of the day your Hilbert space had a tensor product decomposition and the algebra A acted on one factor and A prime on the other, okay, you say, well, the wave function was entangled
Mhm.
and so on. But in your case, you have a single-sided
Yes.
situation. As you emphasized, you don't have the full algebra.
Yes.
Because otherwise there would have been
Exactly.
no complement. But is there a way to say what you found as sort of in terms of entanglement and?
Yeah, that's you mean, for example, can we calculate the entanglement of this small algebra? Is that one question?
Yeah. Is there, even though it's not as algebra proper, it's nearly that. Is there a way to? I mean, let me put it like this. You came close to being able to define a modular operator.
Mm-hmm. The J, you mean, or this?
Delta.
Delta, yeah. I mean, it's. I argued it's given by the CFT Hamiltonian up to 1 over n corrections.
And from there, can you compute an entanglement?
I'm not sure because you know delta is given by the delta is given. It's rho a times rho b minus 1, right? So to calculate the entanglement entropy, you have to somehow be able to divide it, right?
But one thing that you can sometimes do, and that's the more natural object in Tomita, Takesaki, etc., is a relative entropy.
Yes, if you have two states, you mean, or what?
and
Yeah.
I'm not sure how much light it would throw, but
Yeah, that's.
those objects are.
Yeah, I haven't tried to use it, but I agree. It would be it would potentially be useful.
Just to understand a little bit how the code subspace story is working from the point of view of entanglement.
Right, right.
Also, this Tomita Takesaki construction, can it be done in a graded way? Graded by energy?
Meaning, graded by what?
Energy. So let's say you had this creation operators
Mm-hmm.
using which you define your O's,
Mm-hmm.
and then you had operators, right?
Mm-hmm.
So I take first few small energy guys to build my code subspace, okay, and then O tilde should be isomorphic, right? It should have an isomorphic copy in that
Well,
small energy subspace.
if you impose a restriction on the energy, then it's not going to be an algebra, right? I mean, your set is not going to.
Algebra, but if it were an algebra, there would be a correspondence.
Well,
can I truncate it in some sense?
Well, that's what we try to. That's what we try to estimate with Suvrat to some extent. Not at low levels, but at high levels. So we said, suppose you truncate it at some n max, which is very high but smaller than capital N, right? Then, okay, you calculate something.
So now I'm getting the now
Yeah.
with some energy cutoff, if you're
Sorry, energy cutoff or the number of products? Okay, maybe it doesn't matter. Go ahead.
I just confused that this code subspace is not going to be the code subspace. It's not the full, even in the truncated setting, the code subspace is not the full Hilbert space with that cutoff, right?
No.
It's just going to pick up some
Yes.
subspace of that.
Correct.
N square versus n
Correct.
kind of thing.
Yeah.
So in that sense, because in state, in CFT you can create any state just by an operator action and so on. So what is you are also picking some specific operators to create this state, these states, not all the operators of a given energy.
You mean to create the reference state?
Not to create the code subspace till some cutoff, let's say. How are you going to construct the code subspace with a cutoff with what is the choice of operators that you're going to make to?
Well, one point is to create the base state, right? The reference state. To do that, I need to use some very complicated operator which corresponds to that particular microstate. So to be some, you want in the state operator map, you mean, or what? In what picture? I mean, if you do it like that, then it will be some primary with conformal dimension of order n squared. And on top of that, we start acting with the single trace operators of low conformal dimension. Yeah.
On top of that, I guess in an energy band, E to E plus delta E.
The code subspace, that's important again, is not oriented in such a way that it fits into a narrow energy band. It's oriented in the Hilbert space differently. I mean, if the energy goes up, the code subspace is not, let's say, horizontal, right? Because clearly, if you act with O dagger on state, O dagger omega, you increase the energy by omega. So you cannot take a narrow window of energy and put the code subspace in that narrow window. Because you want to be able to do.
Can I think of a problem where I should at the end of the day, the algebra of operators is just an algebra of operators with some small energy, right? Not necessarily large energy.
Yeah.
It's acting on the large energy.
Yeah, right.
But the algebra of operator I can define in some, let's say, truncated way, small energy.
Yeah.
So all operators can be enumerated, let's say in n equals 4 superangles.
Yes.
Then can I essentially think of this problem as constructing this actual O tildes? I mean, it shouldn't be out of grasp, right? Actually constructing these O tildes.
You mean
And O's. I don't know what chooses O's for me also.
O's are the conventional single trace operators, like trace f squared, I don't know, things like that. You can write them in terms of the fundamental fields of the theory. Now, you want to write down the O tildes in terms of the fundamental fields? That's not going to be possible, because in particular they're state dependent. So, I mean, it may be possible in some nonlinear way to do it, but it will be state dependent.
But these operators have some, let's say, finite energy, some small energy, right? Not comparable to n squared.
Yeah, they're matrix
So if
elements.
I exhaust all my operators in O's, how am I going to get any sort of operator for O tilde candidate?
not clear that the final operator will be simple, because you can get finite energy by destroying a lot of things and creating a lot of things.
But it should be some local operator, right?
No. O tilde is not a local operator.
It's not a local
No.
I mean, it could be,
Local in space time.
Yeah.
you see, anything about the vacuum that is finite energy is very simple. But anything about this that's finite energy is not very simple. About this thermal background. You could destroy so much and create so much. You could get something extremely complicated and yet have finite energy.
Now confused a bit. How do I destroy?
You destroy, there are lots of photons around you. Destroy many of them.
Yeah, in CFT.
If you act with O of omega, it lowers the energy, right?
Yeah.
It's like your particles and holes. Like about a Fermi field, you can get very complicated excitations that are finite energy.
Yeah, but so that am I using this case to destroy things? Maybe destroy conformal primary. I'm just thinking very technically.
Yes.
I have a bunch of conformal primaries. Then in order to destroy them, I need to act by case, right? There's special conform transformations.
I think this will be more like you have to do some OPE between some very heavy state and some light operator, and in this OPE there will be some primaries of slightly lower conformal dimension. I don't think you can lower. I mean, this state is primary to begin with, right? It's big state. You can take it to be a primary. It can be a black hole in equilibrium, like in the middle of AdS. It could be a primary. And now you want to.
At the end of the day, just for OT does, I have some finite energy state operator, right?
Yes. Yes.
So I'm just asking, what are my candidates to write that?
Well, you can. It's very simple to write down the matrix elements of this object around the state. But if you want to represent it in terms of the fundamental fields of the theory, it's not going to be simple.
Just to ask you, so bottom line, as far as the information question is concerned, then your point is that, and let's take just the single-sided case, something falls in, you form a black hole. Your point is that these correspond in the CFT to very special states. The states where you form black holes of some mass are very special compared to typical states of that mass.
That's one point, yes.
And for these very special states,
So you can still apply this procedure for these special states at late times.
correct. But just to ask if for these very special states, then you can define these O tilde operators, which are state dependent, but
And he'd say for even more general.
Yeah, O tilde we can define for all for typical states, truly typical states.
that's slightly what I was going to ask. But you don't have a typical state. The black hole, the state formed from collapse,
Yes.
was a special state. And do we have to care about that, or do you
No.
endow your O tilde omegas?
I think.
First of all, I mean,
Uh-huh.
does that whole chain goes through for the special states?
Well, if you some questions are more clear than others. I mean, you can at very late times after the black hole has formed, if you define the O tildes by the same equations and you compute their correlators, you will get that in principle they're able to reconstruct the interior. Now, for example, earlier I drew this Penrose diagram about the typical state with this left region, right? And the motivation to draw it in this way was because the left region is time translation. Sorry, the typical state is time translational invariant. If you have a collapsing black hole, then at early times the black hole is not time translational invariant. There's a star that collapses. So it's not clear right now how we can combine this picture for the typical state to the usual Penrose diagram that you have for the collapsing black hole, where there is a star at very early times.
Yeah, no, but we wait long enough.
Yeah, maybe if you wait long enough, then in some effective way you can think about this region as.
The O tildes
Yeah.
at the upper right-hand corner are similar to yours.
Yeah.
That's what you said.
Yeah, it could even be that even this region, in some effective sense, captures some of the dynamics at late times.
So I'm going to ask an irritating question, maybe we can
Yeah.
discuss over lunch. But this question that many people have brought up, and you've answered, explained to me many times, and somehow I never get in my head.
Uh-huh.
So suppose I have,
Oh, yeah, okay.
you know what I'm going to ask.
If we have a particle here, how do we know it? You mean that?
I mean, you do your construction once on some state, and then take the state where you've got a particle going there, created by your
Okay.
data.
So.
And then do your construction again based on that state.
Right. So I didn't mention a quite important.
Sorry, and the question is now if you've got an infalling observer, naively we have two different predictions. A, that he will die because he hits the particle. There's an asteroid coming, he hits it. B, that he will not die because with the new construction, it should be detected.
Yeah.
So which is the correct?
Yeah. So I did not.
What's wrong?
Yeah, I did not. So we sort of proposed a criterion for this, which I did not mention, which is that this construction is supposed to be done for states psi which are equilibrium states. So, and we define equilibrium states by the condition that they look as time independent as possible from the CFT point of view. So, in particular, single trace correlators should be time independent, up to exponentially small corrections perhaps. And also, as we discussed in the past, correlators involving the Hamiltonian and single trace operators should also be time independent. So, the response to your question would be that if you take that state and you calculate correlators which involve the Hamiltonian, you will find that there's time dependence.
And I suppose this is, maybe we can just discuss it offline, but I'll just ask again. You know, the Hamiltonian is something that you see only on the outside, and you would have expected naively, at least I would have expected naively, at least classically, that the Hamiltonian cannot distinguish what's happening.
So this is something we discussed, right? It's
I somehow don't remember the
The inside operators are built out of the CFT operators.
yeah, but the statement now is that you can detect that asteroid without using the tilde operators, right? If you use the tilde operators, you can definitely detect it. But the question that Siraj is asking is, suppose you before you build up this construction, I give you a state, and it seems to be in equilibrium from the exterior.
All the simple operators look like linear.
Right. But I mean, I think you can, maybe we should discuss the precise computation later, but you can really show explicitly that if you take examples where you have an asteroid on the left side, and you calculate this two-point function that I mentioned, the Hamiltonian times a single trace operator, anti-commutator, you can explain.
Sorry.
Yeah, what is the question?
I thought the O tildes are going to be very complicated
Yes.
in terms of the single trace type of
They are.
operators, right? So just because the statement that on the outside everything looks the same is the statement that expectation values of simple operators look the same, right? But that doesn't mean some expectation value of a chain involving O tildes and O's looks the same.
Right.
Correct.
So what exactly is
So let me ask the question again, just to be clear. Kyriakos and Subrat start with a state that looks sort of nice, and based on that state, they build an interior, which in the absence of any excitation looks empty. Okay, and they use that to predict, I think, that the infalling observer will smoothly sail. Okay, and this sounds great. But now you might the problem that this is state dependent might naively be turned into the following kind of paradox, which is take first, you should be able to do this construction with many different states, provided they have some criteria. One of the criteria is that it's more or less time independent. Time independent as measured by simple things. Okay, so now suppose we take one state that obeys this, and on top of that create an asteroid behind the event horizon using the O tilde operator. Now that state naively looks like from the outside would continue to be more or less identical, and this is what he's disputing, but more or less identical to the
Though, okay.
to the other state, because everything that's happened has happened on the inside.
But please look at the definition of the O tilde operators. There's a non-zero commutator with Hamiltonian, right?
Okay.
Which
Because
implies,
they have energy.
yeah, which implies that this statement that you made that you create something with the O tildes, it should not affect anything of the exterior, is not true at the level of these equations.
Shouldn't it affect just the overall energy of the exterior?
You mean, well, I think you can actually,
Let's say classically, if I had a lump moving.
classically probably it may be true what you say. You would not be able to detect anything more than the energy.
Yes.
But quantum mechanically, if you look at a two-point function which involves a stress tensor, like let's say Hamiltonian and a single trace operator O, but it has to be, as we discussed, it has to be in the form of, for example, an anti-commutator.
Yeah.
Not a I mean, if you take a commutator, it's the time derivative of O, so that's right. But we want to take a Hermitian object, so let's take an anti-commutator.
And that thing.
They can explicitly compute in some examples which I think are controllable, and we can discuss later.
And that is 1 over n? The answer is 1 over n?
It depends how you count, because the Hamiltonian has a natural size of order n squared. So the answer is that correlator should be of order 1. But here we have to take into account the fact that the Hamiltonian itself is order n squared. So it's
I understand.
Yeah.
I understand. And this is the thing I really like to understand intuitively. Because from the effective field theory point of view, it sounds so strange that it's so easy to look inside the event horizon. Do you see what I mean?
Yeah, of course, of course.
You're saying that there's quite simple computation from the outside that tells you whether or not there's something inside.
Yeah, that's.
And that sounds strange.
One possibility that we discussed.
Using very if you had taken a state psi, done what Kyriakos did, and taken another state obtained from psi by acting with a simple single trace operator, there'd be no issue, right?
If you act with a single trace operator, then you
take one typical pure. Actually, you shouldn't. One thing I'm a bit confused is you don't want to be taking typical pure states to describe black holes. But anyway, in your construction,
yes.
You take one typical pure state, construct your state-dependent operators. Take another typical pure state obtained by acting with that original one with a simple single trace operator.
Can I say something?
Yeah, yeah.
If you do that, typically the new state will be out of equilibrium. Typically, usually, unless you.
A wave falling into the black.
Yeah, there's something happening then in this state. So this new state you will get, it will be manifestly non-equilibrium.
Yeah. As we see from AdS CFT, right? It's a black hole and then you've got a pulse curve.
So then, how did you construct your beginning state anyway? Didn't you take a typical pure state?
Typical equilibrium.
Yeah.
Time dependent.
If you act with O on a typical equilibrium state, you do not get an equilibrium state anymore.
So what do you have to do to get another state? It's not so easy.
Not so
Yeah, but I
easy.
was thinking one suggestion.
But it's a very complicated option.
It's very complicated, but it's the suggestion that seems to me, it seems to me that either you have to say that easy observables on the outside can detect the details of what's happening inside, or you're not getting easy prediction. Like you're not getting.
But I think it could also be.
Why is acting with O tilde is small change?
It's not a small change, but it's some new state.
It's a new state.
Now it's a new state with a clear interpretation. It's an interpretation which has an asteroid inside.
What's not clear to me is that whether you can prepare that state you're talking about while not. It could be there are some constraints on the global quantum state of the field, right?
We could do this with this OT.
So what?
Yeah, actually, okay.
What you're saying assumes that.
But what I'm worried about is that his whole construction used a code subspace and so on.
No, but it's based on a certain state.
That state had no restrictions on it?
It had some restrictions, and I want to understand why this new state, where this new state violates that restriction. Because if you are allowed to do the construction based on this new state, then you get two different predictions.
Okay, so I have only one precise statement to make, is that if you try to write down a state with an asteroid, as you said, with a reasonable asteroid, then there are some technical arguments which we can discuss whether you believe them or not. These technical arguments show that the time dependence of these correlators I was talking about on the CFT side, of the form which involve the Hamiltonian, are not in equilibrium.
Right.
So
but isn't that saying that you can quite easily from the outside reconstruct what's
it seems like that, and one possibility that I have not explored, it could not be right, is that it could be that the moment you put the asteroid in the exterior, in the left region, if you want to create this asteroid in the left region, it's not clear whether the quantum state of the field outside the horizon has not to be adjusted in a particular way.
Yeah. So you're saying that you don't
have the freedom to
well enough to create a very localized one.
You don't have the freedom to modify the left state independently without affecting the right.
Which is a violation of effective field theory. Because in effective field theory, you can, right?
Yeah, but yes.
It's relatively large. It's not some exponential violation.
Wait a second. Are you saying it's experimentally detectable, or that in the formalism is such that?
I'm saying that you can do simple calculations from the outside.
But can you do experiments?
Experiments, these anti-commutators.
I don't think you can do experiments. How will you do experiments?
Because anti-commutator?
No, because Oh, wait a second. When you say that you create this asteroid, what do you mean by that? You mean you consider a new state which contains an asteroid, or in some time-dependent fashion you put the asteroid there?
I'm outside the black hole. I want to know whether or not there is an asteroid inside.
Right.
So I do measurements outside the black hole.
Mm-hmm.
Can I use those measurements to tell whether or not?
Yeah. So the question was, could it be that there are some global constraints on the conditions of the state, the entire quantum state? So all these states seem to be coming from the past singularity, right?
Yeah.
So the past singularity, you will get this asteroid, and you will also get the quantum state of the field in the exterior.
Yeah.
Now, it's not clear to me whether there could be some constraints on the type of quantum states that you can get. In particular, if you try to prepare a state which has an asteroid on the left side, you will inevitably have to modify the quantum state in the other side.
Isn't that a very interesting statement about that?
Of course, I mean, that would be extremely interesting, yes.
I'm really confused because I thought the whole point of your tilde operators was that more or less they were complementary to the operators O. That is, they commuted with the operators O. On the state side, like look at that equation, O tilde omega O is the same as O tilde omega on the state side, right?
Yes.
So doesn't that mean, I thought that was the whole point of, doesn't that mean that if you take the state psi and you act with O tilde on it, then seeing the effects of that as different from psi itself are very hard, right?
Well, yeah, but
the
there's,
operators O.
yeah, so the technical point was that you have to look at this equation, which shows that the Hamiltonian does not commute with O tilde by an order 1 amount, right?
But that could just be the changing of the energy of the original state.
Yeah, that could be just that, but I think it's not just that.
So then how does complementarity work? I mean,
What happens?
now I'm really confused. I mean, that means, I mean, these O tilde
Any chance you get joined for lunch and suddenly.
Let's finish. Oh, we can go down.
I should be within the taking him.
Oh, I see. No, sorry.
Yeah.
No, sorry. No, I mean then how? Because don't the O tildes roughly mimic operators inside, which in the Riddler or black hole setting would be space-like separated.
Yeah.
Commute with the O's, and if
But they don't commute with a Hamiltonian necessarily, right? So this is, I mean, you could have said the same thing about a point in the middle of AdS, right? I mean, if you have an operator here, you might think that it commutes with the stress tensor on the boundary, so it should commute the Hamiltonian, but because of the gravitational Gauss law, it's not the case. So we, in terms of gravitational dressing of this, of Gauss law, we're thinking of gravitational Gauss law. We're thinking of these excitations on the left side as being the gravitational Wilson lines are attached to the CFT.
yeah, but that's a very minor coupling just through the constraints. Right?
That's right. That's right.
I think there's much more freedom in what the O's tildes are subject to some fixed energy constraint because you can move them around inside and so on. And so you should have a fair amount of freedom and not be able to detect it on the outside, assure ourselves. If they are doing what you might expect.
What effective field theory expects.
Yeah. It seems too big a violation.
Yeah, the intuition is that you might think there's effective field theory where you can independently prepare this side and that side,
Yeah.
but this side is not real. It's not really real, right? It's not like in the two-sided eternal black hole where you can independently prepare the state as you like. It could be that the state is some sort of approximate space-time region where the initial state that you get here may be somehow correlated to the state that you have in the exterior.
So space-time is coarse enough that you can, that it violates your at least rough classical intuition of general relativity quite significantly.
I don't know. Would you detect it in an experiment, or would you detect that if you could try to consider all possible states and see what possible states you can prepare?
No, in an experiment, just do simple observable measurements outside.
Well, you will see some correlator which is non-zero, right?
Which is non-zero, and you'll
Yeah.
be able to, by doing enough of those.
Yeah, well, if you know this global constraint of how the singularity, for
You've
instance,
got all the theory.
that's right.
You do enough of those, you'll be able to see what was inside.
Yeah, I agree. It sounds.
That sounds like what you should be able to do.
It seems like you don't need the n-point correlators for that, or n-squared point correlators from what you said.
Yeah.
That's the.
There's
that's
simple
the-
things to do. Maybe 1 over n, but not e to the power minus n.
Right. Yeah. So say again. In the thermal field case, you can also address the operators to the left, so that the computer.
Let's all go for lunch.
Thanks.